Welcome back. I hope you had a chance to think about unit cells, and I hope you've got the concept at least reasonably straight in your mind, because it's going to really help understand the properties of crystalline materials that we're going to look at next. So in this section of the video we're going to talk about crystal habit. What is crystal habit? I don't hear you ask. The answer is it's the macroscopic shape of the crystal that we see when we look at that crystal. Think about the sugar cube that we started this lecture with. Imagine that I took one of the crystals of sucrose from the sugar cube and I looked at it, probably under a microscope because it's going to be quite small. I'm probably going to see a cubic shape, and that cubic shape we call the habit of the crystal. Surprisingly, given that the number of unit cells that there aren't actually that many habits that a crystal can grow into, 6, and they're defined by the USP. So on the screen you can see 6 different shapes, starting at the top left: tabular, columnar, which is a fancy way of saying column; equant, which is a fancy way of saying cube; plate, that's not a fancy way of saying anything, it's just a plate; blade; and acicular. Okay, so those are the macroscopic shapes that you might see if you look at crystals under a microscope. You might say to me a number of things. So 1, you might say, well, hang on a minute, sir, surely if the crystal is growing from a unit cell, and the unit cell, for argument's sake, is cubic, then the final crystal shape habit that we look at is also going to be cubic. And that's not actually true. So the shape of the unit cell may be the shape of the final crystal, but it may not, for reasons I'm going to explain in just a minute. So number 1 key point is the unit cell is not necessarily linked to the habit shape. Okay, so you need to split those two things apart. You need to look at the position of the molecules with something like X-ray diffraction in order to work out what the unit cell is, and you need to look at the crystal under a microscope to work out what the habit is, and they are not necessarily the same thing. So that's number 1. And number 2, you might say to me, well, I've seen lots of pictures of crystals in textbooks and stuff like that, and there are some shapes that don't look like one of these 6. So, and that's a fair comment. So you may have seen maybe some crystals with jagged ends, or maybe you've got some side bits going off or something like that. The bottom line is the actual crystal habit is one of these 6. It's just that there'll be a defect. When the crystal is growing, there'll be some sort of defect. So maybe sometimes the molecules don't line up properly, or maybe a different molecule gets involved in the crystal structure. That's quite common actually. So you get a molecule, let's say not of sucrose but of something else, and that causes a defect in the crystal lattice. It may cause an angle to be called like this, and then you get a side arm going off. It doesn't really matter what the cause is. The bottom line is the actual habit is going to be one of these 6, but it might look slightly different because of a defect, especially at the end of a crystal when you may have got bits broken off and it looks very jagged. It's not actually the true crystal itself. The true crystal is going to be one of these 6 shapes. Okay. The other thing is some of these are called names that might be more familiar. So if I picked acicular in particular, I think you might imagine looking at that, that's in the real world that's going to be needle shaped. So sometimes you see crystals described as needle shaped, so obviously long and thin with a kind of pointy end, which is a more common way of describing it. Most people understand what needle shaped is, but I think if I asked you what's an acicular crystal, you probably wouldn't know. So these are the technical names, and in reality sometimes we use non-technical names. Now, why is it the case that a crystal with a particular unit cell doesn't grow into a crystal with a habit which is the same as the unit cell? That's a good question. So the answer is the crystal starts with a unit cell, which is the smallest repeating pattern of molecules that defines where all the molecules are in our crystal. And the actual crystal that we see is comprised of lots of unit cells put together. Can you imagine that if this is my unit cell, and the unit cell is arranged by putting them all on top of each other. So I keep putting one unit cell on top of another, and I keep going. What am I going to end up with? I'm going to end up with a long thin crystal, aren't I? So I'm going to end up with something that's probably needle shaped if all of my unit cells stack on top of each other. Yeah? Let's, for argument's sake, say imagine that the molecules don't stack that way. That's the same unit cell, so it's the same unit cell as before, but now I start to put them together like this. Let's do that, and then do that. Can you imagine, oh that's not very good, can you imagine as that starts to grow, now look what I've got. I've got a completely different structure, almost like a spiral. It's the same unit cell, isn't it? The unit cell is the same, but the way that they've been put together is different. And so I've ended up with a different macroscopic shape. It doesn't really matter how I do this. I can end up with lots of different patterns that I might choose to put my molecules together in. It's one of the reasons I play with Lego so much, as I think you might imagine. Here's another one. Now I've got a true spiral, haven't I? Okay. When I look at these crystals under a microscope, I'm going to see different shapes because the habit is the macroscopic shape of the crystal. It's what I'm seeing when I look down the microscope slide at the crystal. But the crystal has grown by unit cells adding together, and it depends on how the unit cells add together as to what final shape of the crystal I'm going to get. Imagine that we have a material, sucrose is a good example, that has two different unit cells. So here are my two different unit cells. Imagine that the blue one packs together all the unit cells on top of each other, like I had before. I'm going to end up with a needle. So the blue unit cell packs together and the macroscopic crystal is a needle. Imagine that my green unit cell packs together all the molecules on top of each other. It's the same deal. All the molecules, one after the other. What do I get? I get a needle. When I look at these crystals down the microscope, I'm not going to see them in different colours, okay? When I look at these down the microscope, I'm going to see needles in both cases. But the unit cell is different, okay? It's really kind of key to get your head around the concept that when you look at a crystal under a microscope, you can't tell anything about the unit cell of the material. The unit cell is really small. It might be 2 or 3 molecules. The crystal, as you're seeing it on the microscope slide, is absolutely enormous, and so the number of molecules is in the trillions and trillions and trillions. So by the time it gets that big, it's a bit like building something out of absolutely tiny Lego bricks. You're never going to be able to look at the big structure at the end and work out what the size of each of the Lego bricks was. There's no correlation between the habit and the unit cell. Okay, really important to understand that. Why, you might say to me then, is habit so important if it's not related to structure in any way? And the answer is because different shapes of crystals are going to behave differently as you try to process them. So a good example would be if you had acicular crystals or needle-shaped crystals and you were trying to pump those around a factory, and at one point you had a filter. So let's imagine you had a filter with really small holes in. Needle crystals are very difficult to filter because unless they go through the hole exactly like this, the chances are they're going to come down like this and block the filter. So if you're trying to filter crystals, for instance, needles are not very good because they'll get stuck by the filter. Also, sometimes if you've got irregular shapes, they won't flow very well. Sometimes crystals don't compress very well. So it's kind of important that you understand what the shape of your crystal is, as well as what the unit cell is. Sometimes it's almost as important to select your habit as it is to select your unit cell, and I'm going to look at that later on. How can you control the habit of your crystals when you're trying to manufacture something? That's a bit of a grey art, I've got to say, and it's kind of difficult. If you talk to someone who has spent their life trying to grow crystals, they'll tell you it's really difficult to control crystal growth and to control habit. But one way is through solvent selection or by selecting a crystal habit modifier. Now, before I explain how that works, I think it's really important that we look at how do crystals grow in the first place. So, on the screen in front of you, there is a slide to explain the process of crystal formation, and it proceeds in 3 steps. The first one is you have to have the molecules separate. Remember that in a crystalline structure, your molecules have come together to form unit cells, and then they condense to form these big crystals. It's really difficult to start crystallizing if all of your molecules are already in some sort of crystalline material. So we start growing crystals with the molecules completely separate. There's only a couple of ways that you can do that. One is to vaporize the molecules so that they're free floating in air, and the other one is to dissolve them in a solvent so they are separated by solvent molecules. And as I think you might imagine, at least for pharmaceuticals, it's much more common to start with molecules dissolved in a solvent and then allow them to crystallize from a solution. So in this instance, you have to start with a supersaturated solution. What is a supersaturated solution? I don't hear you ask. The answer is, I hope you remember, all molecules have a solubility in a given solvent. Solubility is the maximum number of those molecules that can be dissolved in a given volume of a particular solvent. If you think about it, if you have a solution which is either at its saturation, solubility, or it's below its solubility, there's no drive for the molecules to crystallize because they're equally happy being dissolved in that solvent. There's no need for them to precipitate out of solution. The only way that you can get crystals to grow is to start from a supersaturated solution. That means a solution whose concentration is above the solubility. Another way of thinking about that is to say there's more molecules in solution than there should be, or that the number of solvent molecules can comfortably accommodate. And so really there's a real drive for the excess molecules to precipitate out of solution, and usually they'll form crystals. How do we make a supersaturated solution? It's not as easy as you think, actually. It certainly is not made by simply adding some of your drug substance to your solvent and stirring. That won't work. All that will happen is if you've added enough solid, you'll create a saturated solution and the excess won't dissolve. If you remember the practical from the first year when you measure the solubility of, I think it was either aspirin or paracetamol, you add an excess to water and you allow it to mix for quite a long time, but it doesn't go super saturated. It gets to its saturation and then you filter to remove the excess and measure the concentration. So you can't make a super saturated solution simply by dissolving a lot of material in your solvent. One thing that you can do is you can increase the temperature of your solution, and the reason is because as you increase temperature, usually the solubility increases. So you might take your drug substance, add it to water, add an excess to water, stir, then put it under a Bunsen burner and really heat it up to near boiling. And what will happen is, as it gets near to boiling point, much more will dissolve in the solution. Then you remove the Bunsen burner and let it cool down really slowly back to room temperature. Then what you should have is a relatively unstable but supersaturated solution, because some of those molecules that dissolved at the high temperature, they haven't been able to crystallize out as it's got to the low temperature. So you start with a supersaturated solution, which you might make by heating and then cooling the material. Then what happens? Something has to happen to make these molecules start to come together and crystallize. So the first thing that happens is, and in principle it involves only two molecules, two molecules will come together and they might be able to maybe bounce off each other, but in some instances they'll come together and then they'll form an interaction as the two molecules get close enough and in the right orientation, and they'll stick together and they'll interact with each other, almost to form the unit cell that we talked about earlier. And then another molecule in solution comes along and it forms a third one and a fourth one, and so on. When you've got a small cluster of molecules like this, it's called a nucleus. I'm sure you've heard of that term. So it may well be the case that molecules in solution randomly bouncing off each other, every now and again two molecules will align and stick together and start the basis of a nucleus. That's called primary nucleation. Primary because it's the molecules that you're trying to crystallize that have come together to form this nucleus. Sometimes you can wait a long time for that to happen. I'm sure you've done some organic chemistry preps where the last step is to crystallize your product from solution, and you stood there with it in a beaker and nothing is happening. And so quite often you get told, scratch the inside of the glass with a glass rod. I'm sure you've done that. And the reason that you do that is because it creates small imperfections on the surface of the glass, like really sharp scratches in a way, and they act as nucleation points. It's somewhere for the molecules to kind of condense onto, and so quite often you can scratch the glass, it creates this imperfection, and then the molecules suddenly condense onto that, and then a crystal grows. And that's called secondary nucleation, because you're creating a nucleus out of something else, in that case by scratching the glass. Sometimes it's possible to add a seed crystal. So sucrose, for instance, when it's made commercially, you have a very sticky supersaturated solution of sucrose, more like a sort of caramel sort of thing, and then you add seed crystals of sucrose, and they act as nucleation points for crystal growth. Sometimes even something as simple as dust particles in the air, when they hit your solution, can act as nucleation points and cause crystals to grow. Then when you've got your nucleus, all that has to happen then is molecules that are in solution, they simply condense onto the surface of your growing crystal, and your crystal starts to get bigger. What is the fastest or slowest points of that process? So if you've seen crystals grow in solution, you're probably going to know the answer to this, but forming the nucleus in the first place is really slow. It takes a long time, and you have to get exactly the right molecules coming together in exactly the right orientation to form a nucleus. Crystal growth, on the other hand, almost instant. It's almost like the molecules want to crystallize, but they don't know in what pattern to crystallize. But as soon as you give them a pattern, instantly they will crystallize. So crystal growth happens very fast. Crystal nucleation tends to happen a lot more slowly. If you add seed crystals, you can make something crystallize relatively quickly. If you allow crystal growth to happen naturally, it can take days or weeks or even months. Ask some of the PhD students wandering around the building how long it's taken to crystallize stuff, and you'll just get very sad looking faces. Yeah. So crystal growth is relatively difficult. Why do crystals grow into different habits then, and how can we control what habit we get at the end of crystallization? The why, I think I've said already, because essentially we have unit cells that are packing together, and it depends in which order they pack as to what the final shape of our crystal is. But why does that happen? So to answer that, you've got to think to yourself, well, hang on a minute. There's one thing I've got to remember about molecules, and that is that different molecules have different functional groups. Think about the ibuprofen that we looked at the start. One end of the ibuprofen molecule was an acid, wasn't it? It was a carboxylic acid. And the other end had a relatively small hydrocarbon chain. The thing about crystals is that all the molecules are arranged in a repeating pattern. So what that means is they're all going to be aligned in the same way. So if we think about the ibuprofen molecule, imagine that in the unit cell, the ibuprofen molecules are arranged like this, in this pattern. And that this end is the carboxylic acid end, and that this end is the hydrocarbon end. Because all the molecules are arranged in the same pattern, it means when we look at the face of a particular nucleus or unit cell, doesn't matter, the chemistry on each face will be different. So for ibuprofen, for instance, one of those faces is going to be quite acidic, because all the carboxylic acid groups are pointing up on one face only. If we then look at a different face, it won't be very acidic. It might be very lipophilic or lipophobic. Depends on what the functional groups are. Lipophilic in the case of ibuprofen, because now you've got hydrocarbon tails all pointing in a different direction. So what that means is one face can have completely different chemistry from a different face. And this is really important if you're growing a crystal. So let's say this is your seed, and you've got lots of molecules in solution that want to condense. If you're a molecule and you're coming down and you're going to condense onto this growing crystal, this face might be completely acidic, this face might be completely lipophilic, and it really does matter the chemistry of what's going on as to which face growth is preferred in. To make matters even more complicated, you don't always grow crystals in water. You can grow crystals in any solvent, and as the polarity of the solvent changes, the relative propensity for crystallization on different faces will change. So maybe, for argument's sake, in water, growth on this face is preferred. So every time a unit cell comes down, we get growth on this face. And so we're going to get crystal growth in this direction. Okay? Imagine if I change solvents, I've got the same unit cell, but now growth is preferred on this face, which is kind of difficult with a Lego brick because it doesn't stick on that face. But the next molecules are going to preferentially add onto this face, and then onto this face, and so on. So we're going to get different crystal habits because growth on different faces changes depending on the solvent that you're growing in. Now, if you're not following that, and that's totally fair because it is a tricky concept, I've got to say, there's an example on the slide which I've nicked from the textbook to show you what happens if you get preferential growth on different faces. And this is where my analogy with Lego bricks breaks down because I've started with a hexagon. So top left of the screen you have a hexagon. It's got 6 faces on which crystal growth can occur: A, B, C, D, E and F. For argument's sake, imagine you've got that crystal seed and it's in a solvent on which growth on faces A and D is preferred. What that means, by the way, is it doesn't mean molecules won't grow on or condense onto faces B, C, E and F. It just means that they prefer to condense onto A and D. Okay, so as the crystal gets bigger, more molecules are going to condense onto faces A and D. Fewer molecules are going to condense onto B, C, E and F. The question is, what is the consequence of A and D being the preferred faces for crystal growth? And the answer is, as the crystal grows, more will deposit on A and D, less on B, C, E and F, and so the shape of the crystal starts to change. Can you see that as you go across, you started with a true hexagon, you're starting to move to a distended hexagon as you get more and more growth on the top and bottom faces, and ultimately what will happen is, once the crystal has finished growing, faces A and D are going to disappear. And in this instance we end up with a diamond. The diamond on the right hand side has only got 4 faces and they correspond to B, C, E and F. The faces A and D have actually disappeared. It's one of those slightly confusing things to think about with crystal growth, which is that the faces on which crystal growth is preferred tend to grow out of existence. It's really confusing concept, that, okay? The faces on which crystal growth is preferred tend to disappear. If you're not following that, look at the start. It's a hexagon, A, B, C, D, E and F. All the faces are the same length. Look at the end, the diamond. Faces A and D have disappeared. They were the faces on which growth was preferred. Another way of thinking about this, if you look at the diamond on the end, what are the 4 faces left behind? B, C, E and F. So when you look at a crystal, the faces that you see on your growing crystal are the ones on which growth is not preferred, because they're still there. Yeah, it's slightly confusing this, isn't it? The face on which crystal growth is preferred tend to disappear, and the faces on which crystal growth is not preferred tend to be the ones that remain behind. Okay? Really complicated concept, which, just take a moment to think about it. You can rewind that section and watch it again if you want to, or let's look at what happens if growth is favoured on different faces, because I have another example. So imagine that growth is favoured on faces D and F. So A, B, C and E, not so preferred. What will happen is, every time a molecule comes down to condense onto this growing crystal, it will probably condense onto faces D and F. And so what that will mean is, same thing, you end up with a distended hexagon, because the more molecules are going onto faces D and F than onto the other faces. And what will happen is, in the limit, faces D and F are going to disappear, and we end up with a trapezoid. And again, if you consider what are the faces that are left on that trapezoid, it's A, B, C and E. Faces D and F have disappeared again because they grow out of existence. It's a really tricky concept to get your head around, and I don't blame you if you don't understand it straight off. It's totally fine. Just take a moment to think about it. Maybe talk your way through some of these examples that are on the slide, and you'll see that the fastest growing face tends to disappear. Or when you look at the macroscopic crystal, the faces that you see are the ones on which growth was not necessarily preferred. Yeah. What does this mean for growing different habits? I hope you can see that the seed crystal was a hexagon, A, B, C, D, E and F. And if we manage to get growth to be preferred on faces A and D, we end up with a diamond. If we get faces D and F to be the most popular, we end up with a trapezoid. So how do we do that? We might change the solvent in which we're trying to crystallize. Maybe by changing polarity, because of the chemistry involved, we can get some faces to be preferred and some faces not to be preferred. Sometimes we can add polymers. Polymers are kind of interesting because they're great big molecules, and so they tend to sit on the surface of crystals. So you've got your nice crystal surface, big polymer molecule comes down and absorbs onto that surface. Now you can't get crystal growth on this surface because the polymer is blocking any other molecules coming down. So there's all sorts of ways in which you can set up your crystallization to make growth on some faces favoured and growth on other faces not favoured. And you end up growing a crystal with a different habit. Now, where are we with that? It means you have to remember the habit of the crystal is the shape of the final macroscopic crystal that you're looking at. It's not necessarily related to the unit cell. Two materials with different unit cells can grow to the same habit. Okay? So you can't just look at the crystal under a microscope and say, right, this is definitely this unit cell and this one is definitely that unit cell. There's no direct correlation between habit and unit cell. And we can grow crystals of different habits by changing the conditions under which they are growing. So before we take another break, because I realise this is quite a complicated section, just to finish, on the screen are some pictures of crystals that were grown by one of my PhD students who's now a member of staff and in fact is going to be teaching you on this course. And she called these butterfly crystals, the crystals that are on the screen, principally because they look like butterflies. And here are some other crystals that she grew. These are imaged with scanning electron microscopy. And if you look at those, you can see that they are small plates. Okay, so we look at the crystal to determine what habit it is, but we have to do something like X-ray diffraction to work out what the unit cell is. Right, with that, it's time to stop, get another cup of tea, sit back, maybe chill out and watch a box set or two before you come back again. When we come back, we'll talk about polymorphism.